A pale blue marble hangs alone in the blackness, spinning completely on its side. What secrets does this distant, tilted ice giant hold that continues to baffle the world's top scientists? This is Uranus, the solar system's ultimate oddball, a world defined by its extreme lean, its whisper-faint rings, and a mysterious, frozen heart that refuses to radiate heat. It is a planet that seems to break the rules at every turn. By the end of our journey, you will know the 25 greatest unsolved puzzles that make Uranus a keystone to understanding planets everywhere. We will explore a moon scarred by unimaginable violence and ask why this ice giant is so eerily cold. Are you ready to become a cosmic detective? That dramatic 98-degree lean is not just a quirk, it is the solar system's most profound planetary identity crisis. While Earth enjoys a gentle 23.5-degree tilt, giving us our seasons, Uranus has been knocked completely onto its side. Picture its north pole pointing almost directly at the Sun, with the entire planet rolling around its orbit like a celestial bowling ball. This is our first and perhaps greatest mystery, the extreme axial tilt. For a world to end up in such a state, astronomers point to a violent, formative event, a cataclysmic collision in the early chaos of the solar system. The leading theory suggests an object roughly the size of Earth, a protoplanet, slammed into the young Uranus with such force that it literally tipped the world over. This was not a glancing blow, but a direct planet-reshaping impact that likely melted the interior and set its unique rotation in stone, or rather in ice. The consequences of that ancient violence are written across the Uranian year. A single orbit around the Sun takes 84 Earth years, and thanks to that tilt, each pole experiences a summer that lasts for 42 years of continuous sunlight, followed by a winter of 42 years of utter darkness. Imagine a sunrise that lasts for 4 decades and a sunset that lingers just as long. The atmospheric dynamics on a world with such bizarre seasons are almost impossible for us to fully model. Yet this collision theory, while compelling, leaves glaring questions in its wake. What was the exact nature of this colossal impactor, and where did it come from? More puzzlingly, why did this apocalyptic event not utterly destroy or drastically alter the orbits of Uranus's major moons? They orbit neatly around the planet's equator, as if the titanic impact never happened. This discrepancy has led some scientists to wonder if a series of smaller impacts could be responsible, or perhaps complex gravitational interactions with other giant planets during the solar system's youth. The truth is, we simply do not have a complete answer for why Uranus lies on its side, a silent monument to a forgotten cosmic catastrophe. This profound lack of internal warmth leads us directly to our second great mystery, the missing internal heat. To understand just how strange Uranus is, we must look at its sibling Neptune. Both are classified as ice giants, worlds of similar size and composition, born from the same cold outer reaches of the solar system. Yet they behave in starkly different ways. Neptune, like Jupiter and Saturn, is a powerhouse. It radiates about 2.6 times more heat than it receives from the distant Sun, glowing with a fierce internal energy that drives its wild, supersonic winds and churning blue atmosphere. Uranus, by shocking contrast, shows almost no excess internal heat at all. It is thermally lethargic, radiating back into space only about as much energy as the feeble sunlight provides. This makes Uranus, not Neptune, the coldest planet in our entire solar system, with cloud-top temperatures plunging to a bone-chilling -371 degrees Fahrenheit, despite Neptune being farther from the Sun. So where did its heat go? One compelling theory points back to that ancient cataclysm that knocked it over. The titanic impact may have been so violent that it essentially blasted away the planet's primordial heat reservoir, scattering it into space and leaving behind a cold, stratified interior. Imagine a pot of soup that is violently stirred, then left to sit. The layers separate, and convection, the process that moves heat from the core upward, grinds to a halt. This is what scientists suspect happened inside Uranus. Its interior may be so orderly, so stagnant, that the heat from its rocky core simply cannot find a way to rise to the surface. It is trapped forever in the deep, leaving the outer layers in a perpetual deep freeze. This profound heat deficit has dramatic consequences for the Uranian atmosphere. Without that internal engine to stir the pot, its weather systems are thought to be far more subdued and sun-driven than Neptune's tempestuous chaos. The seasons, bizarre as they are with 42 years of sunlight, may create slow, monumental waves of climate change we are only beginning to comprehend. The mystery of the missing heat is not just a thermal curiosity. It is the key to understanding why this ice giant is so eerily and uniquely quiet. But this profound quiet and cold extends far beyond the planet's cloud tops into the space immediately surrounding it. Orbiting Uranus is a system of rings so dark and subtle they remained completely hidden from Earth until 1977. This is our third great mystery, the faint and dusty ring system. Unlike the brilliant, sprawling icy banners of Saturn, which reflect sunlight with dazzling intensity, the rings of Uranus are narrow, whisper-thin, and almost charcoal black. There are 13 known rings, most no more than a few miles wide, composed of particles ranging from boulders down to fine, powdery dust. If you could stand within them, they would likely appear as a series of dark, sooty bands against the starry backdrop, more akin to lanes of cosmic gravel than jewels of ice. Their profound darkness is the central puzzle. What are they made of that absorbs so much light? The leading theory points to radiation darkening. The rings are likely composed of water ice like Saturn's, but out at Uranus's distance, that ice is heavily bombarded by charged particles and cosmic radiation. This relentless assault can break apart water molecules and reform them into complex, dark organic compounds, essentially baking the ice into a tarry, carbon-rich crust. Another possibility is that the rings formed from the debris of a shattered moon or captured object that was already rich in these dark materials, like a primordial ball of rock and frozen methane. The rings are not static, however. Their sharp, well-defined edges suggest the presence of unseen architects, small shepherd moons that orbit within the gaps, their gravity gently herding the ring particles and preventing them from spreading out. Many of these tiny custodians are predicted by our models of orbital dynamics, but they remain undiscovered, hidden in the profound darkness. Our best glimpse into this shadowy system came during a rare celestial alignment in 1986, a ring plane crossing. As Uranus's rings tilted edge onto Earth, they vanished from our view, but in doing so, they allowed astronomers to detect faint new rings and structures previously lost in the planet's glare. It was a fleeting opportunity to map the architecture of this dark realm, revealing a system both delicate and ancient, a silent record of collisions and captures from the solar system's violent youth. This profound darkness extends even to the forces you cannot see, where Uranus holds yet another bizarre card. The planet possesses one of the strangest magnetic fields in our entire solar system. On Earth, our magnetic field is relatively orderly, with north and south magnetic poles roughly aligned with our geographic poles of rotation. It is like a simple bar magnet running through the planet's center. Uranus, true to form, shatters this model completely. Its magnetic field is tilted by about 59 degrees from its axis of rotation, and it is not even centered on the planet's core. Instead, the magnetic field source is offset by nearly a third of the planet's radius, as if the magnetic heart of Uranus is beating wildly off to one side. This creates a truly chaotic situation. As the planet rolls on its side through its 17-hour day, this lopsided, tilted magnetic field tumbles through space like a poorly thrown football. For any hypothetical compass on Uranus, north would be a wildly moving target, swinging through the sky in a dizzying daily dance. What could possibly generate such an asymmetric, chaotic force? The leading theory points to the planet's interior, but not to a familiar molten iron core like Earth's. Scientists believe the magnetic dynamo of Uranus is generated much closer to the surface, within a slushy, electrically conductive ocean. This is no ordinary water. Under the immense pressures inside the ice giant, water mixed with ammonia and methane forms a hot, dense, and ionized fluid that can conduct electricity. It is a bizarre state of matter sometimes called superionic ice, where water molecules break apart and oxygen ions crystallize into a lattice while hydrogen ions flow freely through it like a metal. It is within this churning, conductive slush, somewhere between the solid core and the gaseous atmosphere, that the Uranian magnetic field is thought to be born. The dynamo process here is fundamentally different and poorly understood, likely shaped by the unique boundaries and flows of this pressurized ocean, resulting in a magnetic field that is as off-kilter as the planet itself. This asymmetry is not just a curiosity. It has real consequences, funneling charged particles onto the atmosphere in unpredictable patterns and creating an auroral display that would look nothing like our serene polar lights. This off-center magnetic field interacts with a world that, from a distance, looks deceptively calm. The dominant visual feature of Uranus is its serene, almost uniform cyan blue hue, a placid marble that seems to lack the dynamic storms of its siblings. This bland beauty is our fifth great mystery, the atmospheric composition and color. The basic recipe is familiar for a gas giant, a deep atmosphere of hydrogen and helium. But it is the trace ingredients that paint the picture. About 2.3% of the Uranian atmosphere is methane gas, and this simple molecule is the artist behind the planet's signature color. High in the atmosphere, methane acts like a celestial filter, strongly absorbing the red wavelengths of sunlight and scattering the blue back into space. The result is that beautiful, pale aquamarine globe. Yet the upper atmosphere appears remarkably smooth and featureless in most observations, especially compared to the vibrant, contrasting bands and giant dark storms of Neptune. Why is there such a dramatic difference? The answer may lie in the deep freeze of Uranus. Its profound lack of internal heat means there is less energy to drive the large-scale convection and turbulence that create visible cloud features. The weather, if it exists prominently, may be happening much deeper, hidden beneath a thick global haze. This haze itself is a chemical mystery. Sunlight triggers complex reactions in the methane-rich atmosphere, a process called photochemistry. Over eons, this has likely created a soup of heavier hydrocarbons like ethane and acetylene, which can condense into fine, smog-like particles that shroud the entire planet in a diffuse, high-altitude veil. This haze scatters light uniformly, washing out contrasts and giving Uranus its soft, featureless appearance. Even more intriguing is what lies beneath this haze. In 2018, spectroscopic studies confirmed the presence of a cloud deck no one would want to smell: hydrogen sulfide ice. This is the compound that gives rotten eggs their distinctive odor. Its detection was a major clue, as it differs from the ammonia ice clouds found on Jupiter and Saturn, marking a clear chemical divide between the gas giants and the ice giants. The existence of these fetid clouds tells us that the Uranian atmosphere is stratified into distinct layers, with different ices condensing at different altitudes based on temperature and pressure. The great puzzle is what dynamic processes are churning within these hidden layers. Are there colossal storm systems, vast jet streams, or slow climatic waves playing out far below the serene blue haze, completely invisible to our telescopes? The bland face of Uranus may be the ultimate cosmic poker face, masking a world of complex and hidden meteorological drama. That serene blue face is a master of deception. Beneath its placid haze, Uranus is a world of staggering seasonal extremes, and this brings us to our sixth great mystery, the bizarre seasonal weather patterns. Remember, each pole endures 42 years of continuous sunlight followed by 42 years of utter darkness. This creates a climate cycle unlike anything else we know. For decades, our only close-up view came from Voyager 2, which flew by in 1986 during the Southern Hemisphere's high summer. It saw a quiet, featureless world, reinforcing the idea of a dormant atmosphere. But Uranus has since thrown that assumption into chaos. In 2014, as the Northern Hemisphere approached its spring equinox, ground-based telescopes equipped with advanced adaptive optics pierced the haze and saw something astonishing. Gigantic, bright storms were erupting in the northern mid-latitudes. These were not small features. One storm system observed by the Keck Observatory was a colossal convective plume, a towering mass of methane ice crystals so vast it could span an entire continent on Earth. Then, in 2022, the Hubble Space Telescope captured another monster, a brilliant polar cap of swirling clouds dominating the North Pole. This was a planet coming violently to life as sunlight returned to a hemisphere that had been in frozen darkness for decades. The sheer scale of these features is baffling. With so little internal heat to act as an engine, what is powering such titanic outbursts? The leading theory points to the profound depth of the Uranian atmosphere. Seasonal sunlight, after such a long polar night, may finally penetrate deep enough to reach layers where methane can condense and form clouds. This solar heating, though faint, might be triggering colossal convective upwellings, like a pot of water finally beginning to simmer after a very, very long time on a low flame. The atmosphere itself, with its complex layers of haze and ice, may act as a thermal capacitor, slowly storing energy over decades before releasing it in sudden, dramatic outbursts. This suggests a world with a profoundly delayed climate response, where the weather we see today might be the result of solar energy absorbed half a century ago. The great puzzle is understanding the intricate, slow-motion dance between the weak sun, the deep atmosphere, and the almost absent internal heat. It forces us to ask what other climatic surprises are still brewing in the darkness of that 42-year winter, waiting for their own long-delayed spring. These colossal seasonal storms are not the only actors on the Uranian stage. Orbiting this tilted world is an entire ensemble of strange and varied moons, 27 in total, each named for characters from the works of Shakespeare and Alexander Pope. Their existence presents our seventh great mystery, the origin and evolution of the Uranian moons. The five largest, Miranda, Ariel, Umbriel, Teutonia, and Oberon, are worlds unto themselves, and their very nature challenges our understanding of how planetary systems are built. The central question is one of birth. Did these moons form peacefully from a disk of gas and dust that swirled around the infant Uranus, much like the planets around the Sun? Or are they cosmic refugees captured by the ice giant's gravity from the chaotic outer solar system? The evidence is puzzlingly mixed. Their orbits are mostly circular and aligned with the planet's equator, which strongly suggests a calm co-formation from a circumplanetary disk. But that tidy story clashes violently with the titanic impact thought to have knocked Uranus onto its side. Such a catastrophic collision should have vaporized any existing moons or sent them careening into wildly different orbits. So did the moons form after the great tipping from the debris of that very impact, or did they somehow, miraculously, survive the apocalypse? Their varied faces tell a story of incredible violence and renewal. Take Miranda, the innermost of the major moons. It is a fractured, Frankenstein's monster of a world. Voyager 2's images revealed a jumbled landscape unlike any other, a chaotic patchwork of giant fault canyons, ridged plains, and bizarre, wedge-shaped regions called coronae. One of these features, a vast chevron pattern of light and dark grooves, looks as if the moon was torn apart and hastily glued back together. The cliffs of Uranus are staggering, with faces estimated to be 20 kilometers high, nearly 10 times the depth of the Grand Canyon. This suggests a history of being shattered by a massive impact, only for its own gravity to pull the pieces back into a rough, scarred sphere. The other large moons show their own scars. Ariel appears the youngest and most geologically active, its surface crosscut by an extensive network of fault valleys, suggesting it expanded and cracked as its interior froze long ago. Umbriel, by contrast, is ancient and dark, its face heavily cratered and seemingly dormant, while Teutonia and Oberon show hints of past tectonic activity and possible subsurface oceans frozen in time. Their compositions, a mix of rock and water ice, are consistent with forming from the same primordial material as Uranus itself. Furthermore, some of the moons are locked in orbital resonances, their orbits harmonically linked by gravity, a strong clue they have peacefully evolved together over billions of years. The great unresolved tension is this: how do we reconcile the moon's orderly, co-formed orbits with the planet-shattering violence required to create Uranus's extreme tilt? The moons of Uranus are a celestial paradox, a seemingly serene family whose very existence whispers of an ancient, unimaginable cataclysm. Miranda is a world that defies every expectation. It is the smallest of Uranus's major moons, barely 500 kilometers across, yet it boasts the most violently tortured landscape ever seen. This is not a place of gentle craters or smooth plains. Miranda looks as if it was shattered by a cosmic hammer and then carelessly reassembled by a child. Its surface is a jarring patchwork of at least 3 distinct types of terrain, smashed together in a chaotic geological jigsaw puzzle. Vast, ancient cratered regions lie abruptly beside smoother, younger plains, which themselves border the moon's most iconic and mysterious features, the coronae. These are immense oval-shaped regions, hundreds of kilometers across, marked by concentric patterns of ridges and grooves that resemble giant, frozen ripples in rock and ice. One of them, named Inverness Corona, forms a vast chevron of light and dark bands that dominates an entire hemisphere. Between these bizarre features run networks of canyons so profound they make earthly geography seem miniature. Uranus is a staggering cliff face, a fault scarp estimated to be 20 kilometers high. If you stood at its top, the cliff's base would vanish into the darkness below, a sheer drop nearly 10 times deeper than the Grand Canyon. The very existence of such extreme geology on such a tiny, cold world is our 8th great mystery. How could a moon with so little internal heat and gravity muster the energy to tear itself apart so spectacularly? Scientists are drawn to 2 dramatic, competing theories. The first is a story of apocalyptic violence. In the distant past, Miranda may have been struck by another sizable object, an impact so colossal it completely shattered the moon into fragments. Over time, Miranda's own gravity would have pulled those pieces back together, but the reassembly was messy and incomplete, leaving a Frankenstein's monster of a world with its internal layers scrambled and its surface a permanent record of that trauma. The second theory is one of internal fire. Miranda's orbit around Uranus is not perfectly circular. In the past, gravitational tugs from neighboring moons like Ariel and Umbriel may have locked it into an orbital resonance, a rhythmic gravitational dance. This would have flexed Miranda's interior repeatedly, generating intense tidal heating. This heat could have been enough to partially melt its icy mantle, causing massive convective upwellings that broke through the crust, creating the coronae as vast, frozen bubbles of upwelled material before the interior cooled and solidified once more. The core of the mystery lies in Miranda's size. It is simply too small to have retained significant heat from its formation, and its tidal heating would have needed to be extraordinarily powerful to cause such global disruption. Yet the evidence of that disruption is written across its face in 20-kilometer-high cliffs and continent-sized ripples. Miranda stands as a stark reminder that even the smallest, coldest worlds in our solar system can hold records of titanic, transformative forces we are still struggling to fully comprehend. Miranda's shattered surface speaks to the immense gravitational forces at play in this system, forces that sculpt not just moons but the very fabric of space around Uranus. The planet's faint rings are not static decorations, they are dynamic structures constantly shaped and confined by unseen sentinels. This brings us to our ninth great mystery, the shepherd moons and ring dynamics. The architecture of this dark ring system is incredibly precise. Most of the 13 rings are razor-thin, some only a few kilometers wide, and they maintain remarkably sharp, well-defined edges over vast distances. Such precision in the chaos of space does not happen by accident. It requires architects. Enter the shepherd moons, tiny worlds whose gravity acts as a cosmic traffic cop. The brightest and outermost ring, the Epsilon ring, is a perfect textbook example. It is flanked by two small moons, Cordelia on its inner edge and Ophelia on its outer edge. As these moons orbit Uranus, their gravitational pull gently herds the ring particles between them. Cordelia tugs inward, Ophelia tugs outward, and together they prevent the ring material from either drifting into the planet or dissipating into space. This delicate ballet maintains the ring's narrow, ribbon-like structure, but the mystery deepens when we ask, are Cordelia and Ophelia alone? Our models of orbital dynamics suggest they cannot be. To explain the crisp boundaries of all the rings, astronomers predict a whole population of undiscovered moonlets, each perhaps only a few kilometers across, nestled within the gaps and cruising along the edges of these dark bands. These tiny shepherds would be far too small and dark for our current telescopes to spot from Earth, making them ghostly presences inferred only by their gravitational handiwork. Even more intriguing is the possibility of ring arcs, dense clumps of material within a ring that orbit together like a celestial school of fish. Neptune's rings famously contain such bright arcs, and while none have been definitively confirmed at Uranus, their existence is a tantalizing possibility. The formation and longevity of these structures pose a profound puzzle. How can such delicate arrangements, mere lanes of dust and gravel, survive for billions of years? They face constant threats, from the subtle gravitational nudges of the larger moons to the relentless bombardment by micrometeoroids and radiation, which should slowly grind the particles down and cause the rings to spread out and fade. Their persistence suggests a delicate, ongoing balance, a system where perhaps new material is occasionally replenished by the collisions of those very same hidden moonlets. The stability of Uranus rings is a cosmic high-wire act, one that requires incredibly precise orbital calculations to understand. It is a silent, gravitational symphony conducted by moons we cannot even see, playing out in the darkness around a tilted giant. The bizarre magnetic field of Uranus forces us to look inward to the very heart of what makes an ice giant. This brings us to our 10th great mystery, the composition of the interior ice. The term itself is deeply misleading. When astronomers call Uranus an ice giant, they are not describing a frozen, solid world. Far from it. The ice in this context refers to a hot, dense, and electrically conductive fluid mantle that lies beneath the gaseous hydrogen and helium atmosphere. Imagine a planetary ocean of staggering proportions, but one where the water is mixed with ammonia and methane and subjected to pressures millions of times greater than Earth's atmosphere. At such extremes, the familiar rules of chemistry and physics break down. Water cannot remain simply H2O. It transforms into exotic, superheated slush where molecules are torn apart and reassembled by the sheer force of the planet's gravity. The central puzzle is determining the exact state and layering of this deep, global ocean. Is it a relatively uniform, churning fluid from top to bottom? Or is it stratified into distinct shells like the layers of a cosmic onion, each with its own bizarre properties? Laboratory experiments here on Earth using powerful diamond anvils to crush tiny samples point to one particularly strange possibility, a phase called supersonic water. In this state, the immense pressure forces the oxygen atoms from water molecules to lock into a rigid crystalline lattice, like the structure of a solid. Meanwhile, the hydrogen ions break free and flow freely through this oxygen cage, like electrons moving through a metal. This creates a paradoxical material that is simultaneously solid and fluid, a conductive lattice that could generate electrical currents simply by the motion of the planet's rotation. The existence of a vast layer of supersonic water within Uranus could be the key to explaining its chaotic, off-center magnetic field. A dynamo generated within such a material, confined to a specific shell and not the core, would naturally produce a magnetic field that is tilted and offset. Furthermore, the way heat is transferred through this exotic mantle, whether by sluggish convection or slow conduction, would directly impact the planet's profound thermal lethargy. Solving the mystery of the interior ice is not just about cataloging exotic chemistry. It is about reading the hidden blueprint of the planet's power, magnetism, and very evolution, written in a language of pressure and phase that we are only beginning to decipher. The profound quiet of Uranus is a masterful illusion. Beneath that placid blue haze, the atmosphere is a river of motion, a torrent of wind that defies the planet's frozen heart. This is our 11th great mystery, the anomalous wind speeds. For a world with almost no internal heat to drive its weather, Uranus boasts some of the most powerful zonal winds in the solar system. By tracking the faint movement of methane cloud features, scientists have clocked these jet streams racing in the direction of the planet's rotation at speeds up to 900 kilometers per hour at the mid-latitudes. That is over 560 miles per hour, faster than the most powerful hurricanes on Earth. The sheer force of these winds presents a fundamental puzzle. On Earth and Jupiter, the engine for our weather is the heat differential between the warm interior and the cold outer space, driving massive convection cells that become twisted by planetary rotation into jet streams. But Uranus lacks that fiery engine. Its interior is profoundly cold and stratified. So what is whipping its upper atmosphere into such a frenzy? The stark contrast with its sibling Neptune deepens the mystery. Neptune, with its powerful internal heat, has even faster winds, some reaching supersonic speeds of 2,000 kilometers per hour. Its turbulent, storm-filled atmosphere makes logical sense, a pot boiling vigorously from a flame below. Uranus is like a pot on a cold stove, yet its surface is still simmering violently. How is that possible? The leading theory points to an incredibly thin skin of weather. The winds we observe may be confined to only the very uppermost layer of the atmosphere, a shallow veneer of activity riding atop a deep, stagnant, and quiescent interior. In this view, the driving force is not internal heat, but the faint energy of sunlight. After a 42-year polar night, the returning sun may heat the upper atmosphere just enough to create dramatic temperature contrasts between the dark and sunlit hemispheres. These contrasts could generate the immense pressure gradients that accelerate the winds to such astonishing speeds. Yet this explanation only leads to another, deeper question of mechanics. How is the momentum for these winds generated and sustained in such a thin layer? On a planet with a deep, churning interior, momentum can be transferred from the core outward. But if Uranus's interior is calm, the winds must be self-contained, a phenomenon of the atmospheric skin alone. The mechanism for this, how energy and motion are transferred and focused into narrow, screaming jet streams without a deep engine, remains completely unknown. It suggests that the serene blue face of Uranus is not a mask for hidden turmoil below, but rather a breathtakingly thin and violent mask all by itself, a gale force whisper over a frozen, silent abyss. That gale force whisper over a frozen abyss converges at the planet's crown, sculpting one of its most enigmatic features. High above the north pole of Uranus, a brilliant, compact swirl of clouds dominates the view, a stark white vortex against the pale blue backdrop. This is the polar vortex and cloud cap, our 12th great mystery, a structured atmospheric feature that seems utterly out of place on such a thermally lethargic world. Recent infrared observations from telescopes like Keck and Hubble have pierced the haze to reveal this swirling maverick in stunning detail. It is not a loose collection of storms, but a coherent, persistent whirlpool centered directly on the pole, reminiscent of the more famous polar vortices on Saturn and Earth, but with its own Uranian strangeness. Its very existence is a profound puzzle. How does such a tightly organized, long-lived feature maintain itself in an atmosphere supposedly lacking the internal energy for vigorous, sustained weather? On Earth, our polar vortex is a product of the planet's rotation and the temperature contrast between the equator and the poles. On Saturn, the incredible hexagonal jet stream is a stunning example of stable atmospheric dynamics on a rapidly spinning world. Uranus spins quickly, completing a day in about 17 hours, and this rotation is likely the primary architect of the vortex. As the atmosphere flows poleward, the planet's spin corkscrews the air into a tight, swirling pattern, trapping it over the pole. But rotation alone cannot explain its persistence and vivid cloud structure. The key may lie in the extreme Uranian seasons. This bright vortex emerged and intensified as the North Pole moved out of its 42-year-long winter and into continuous sunlight. For decades, the pole was in frigid darkness, a deep freeze that likely created a stark temperature gradient between the cold pole and the slightly warmer lower latitudes. Now, with the sun finally shining, the polar atmosphere is being slowly heated from above. This unique heating, combined with the planet's rapid sideways spin, may be channeling and focusing atmospheric energy directly to the pole, creating a self-sustaining engine for the vortex. The bright clouds themselves are likely crystals of methane ice, condensing as the air swirls upward and cools in the center of the whirlpool. The great unanswered question is whether this vortex is a permanent fixture, waxing and waning with the seasons, or a transient phenomenon that will dissipate as the polar summer deepens. Studying this solitary, swirling sentinel is more than planetary observation. It is a fundamental experiment in fluid dynamics. It shows us how energy, even the faintest trickle of sunlight, can be organized by a planet's tilt and rotation into a stunningly precise structure, a beacon of order in the frozen chaos of an ice giant sky. That brilliant polar vortex is not the only storm hiding in the pale blue. On rare occasions, a dark blemish appears, a shadowy eye staring out from the methane haze. These are the atmospheric dark spots of Uranus, our 13th great mystery. They are the ice giant's version of a hurricane, but one that behaves in ways that defy our expectations. Unlike the famous, long-lived great dark spot of Neptune, which persisted for years, the dark vortices of Uranus are fleeting phantoms. The most notable one was spotted by the Hubble Space Telescope in 2006, a compact, dark oval swirling in the northern hemisphere. Scientifically, these features are anticyclonic storms, high-pressure systems where air is slowly sinking. On Earth, high pressure typically brings clear, calm weather. But on Uranus, in the upper cloud deck, this sinking motion seems to clear away the bright methane ice haze, opening a transient window to a darker, warmer layer below. That is why they appear as dark holes against the brighter background. Their very existence is puzzling. With so little internal heat to drive powerful convection, what force suddenly punches these holes in the cloud deck? Their rapid formation and even quicker dissipation is the core of the enigma. A dark spot might emerge over a matter of days or weeks, only to vanish just as suddenly, leaving no trace. This transient nature makes them astronomically frustrating to study. You cannot predict when one will appear, and by the time you point a major telescope at Uranus, it might already be gone. Catching them requires constant vigilance, a planetary watch conducted by Earth-based observatories and Hubble during its precious allocated time. The leading theory suggests they are born from instabilities in the powerful zonal wind jets. When these 900 km/h rivers of air encounter a shear or a disturbance, they might twist into a localized vortex, much like an eddy forming in a fast-moving stream. The mystery deepens when we consider the seasons. Are these dark spots more common during the equinoxes, when sunlight is distributed evenly across the planet, or do they erupt as a hemisphere emerges from its decades-long winter? The data is too sparse to say. Each dark spot is a brief, violent exclamation point in an otherwise quiet atmospheric sentence, a reminder that for all its serene appearance, Uranus is a world capable of sudden and mysterious outbursts. These fleeting dark spots are whispers from an atmosphere entangled with invisible forces far above. The chaotic magnetic field of Uranus does not just exist in isolation. It carves out a vast and turbulent bubble in space known as the magnetosphere. This protective magnetic envelope, shaped by the planet's off-kilter, tumbling field, is our 14th great mystery. Around Earth, our magnetosphere is a relatively symmetrical shield, deflecting the solar wind in a smooth, comet-like tail. At Uranus, the shield is profoundly lopsided and constantly in motion. Because the magnetic field is tilted by 59 degrees and offset from the planet's center, the entire magnetosphere wobbles violently with each 17-hour rotation. Imagine holding a flashlight sideways and spinning in a dark room, the beam swinging wildly, illuminating different patches of the wall. That is the Uranian magnetosphere, a chaotic cavity in the solar wind that changes shape by the hour. This bizarre configuration has direct and puzzling consequences, most visibly in the planet's auroras. On Earth, the northern and southern lights dance in neat rings around our magnetic poles. On Uranus, the auroras are faint, diffuse, and utterly disorganized. They do not crown the poles but instead appear as scattered, glowing patches that flicker in middle latitudes, following the magnetic field lines as they plunge into the atmosphere in unpredictable locations. They are the ghostly signature of charged particles from the solar wind being funneled along those chaotic magnetic pathways. Even more telling are the planet's radio emissions. All giant planets with magnetic fields crackle with radio waves generated by charged particles spiraling along magnetic field lines. Jupiter's radio roar is a dominant signal in our solar system. Uranus, by contrast, is a weak and irregular whisperer. Its radio emissions are sporadic and lack the powerful, periodic bursts we see elsewhere. This radio silence is a profound clue. It suggests that the processes which accelerate particles to high energies within the magnetosphere are inefficient or fundamentally different. The tumbling, asymmetric field may be too disordered to create the stable acceleration zones found at other planets. The solar wind, a steady stream of charged particles from the Sun, slams into this lopsided magnetic bubble in a uniquely messy interaction. Instead of flowing around a steady obstacle, it encounters a target that is constantly shifting its orientation. This likely causes the magnetosphere to reconfigure itself dramatically with each rotation, potentially even opening temporary gaps that allow the solar wind to directly buffet the upper atmosphere. And this entire chaotic system has a seasonal cycle. As Uranus orbits the Sun, the orientation of its rotational axis, and thus its tumbling magnetosphere, relative to the solar wind, changes over an 84-year period. This makes the Uranian magnetosphere a unique natural laboratory, one where we can observe how a planetary magnetic shield behaves under every possible angle of attack across a human lifetime. The weakness of its radio voice is not a sign of a dying world, but a testament to its profound strangeness, a magnetic fingerprint unlike any other in our celestial neighborhood. The profound radio silence of its magnetosphere hints at a world of hidden stillness, but that quiet might be a cloak for one of the solar system's most tantalizing possibilities. Could liquid water, the essential ingredient for life as we know it, exist in the deep freeze of the Uranian system? This is our 15th great mystery, the possibility of a subsurface ocean. We are not looking at the planet itself this time, but upwards at its largest moons, Titania and Oberon. These are worlds nearly the size of our own moon, massive enough to hold onto internal secrets. The conventional view of these distant moons is one of frozen, geologically dead spheres. But a revolution in planetary science has taught us that ice is not always a prison, it can be an insulating blanket. The key is internal heat, and these moons may have two potential sources. First, deep within their rocky cores, radioactive elements like uranium and thorium decay, releasing a slow, steady warmth that has persisted for billions of years. This gentle geothermal heat trickling upward could be enough to maintain a layer of liquid water at the boundary between the rocky core and the icy mantle, especially if that water is mixed with ammonia, a powerful antifreeze. The second, more dramatic source is tidal heating. Today, the orbits of Titania and Oberon are stable and circular, so tidal flexing is minimal, but the past was likely far more chaotic. In the early solar system, gravitational interactions could have locked these moons into orbital resonances, a rhythmic dance where their gravitational tugs repeatedly squeezed and stretched each other's interiors. This process generates immense friction and heat, enough to melt vast quantities of ice and potentially create global subsurface oceans that may have persisted for eons. The surface geology we see from Voyager's old images offers tantalizing, if cryptic, clues. Titania shows enormous canyon systems and smooth plains that hint at tectonic stretching and possible resurfacing by slushy material from below. Oberon, while more heavily cratered and ancient, also possesses mysterious dark material in its largest craters, which some scientists speculate could be organic rich sludge that erupted from a once warm interior. So how could a future mission prove an ocean exists? It would listen for a magnetic whisper. A spacecraft flying close to one of these moons could detect a subtle, induced magnetic field. As Uranus's chaotic magnetic field sweeps over a moon, it would generate electrical currents in a conductive layer beneath the surface, and a global ocean of salty water is an excellent conductor. The detection of this magnetic signature would be the smoking gun. Alternatively, detailed imaging might reveal very specific surface fractures or smooth terrains that point to the crust floating on a liquid layer, much like the icy shells of Jupiter's moon Europa or Saturn's Enceladus. The implications are staggering. If even one of these distant dark moons holds a hidden sea, it dramatically expands the habitable real estate of our solar system. It means that the conditions for life are not confined to a narrow, sun-warmed band around our star, but can exist in the profound cold, powered by the slow decay of rocks and the memory of ancient gravitational dances. The Uranian system, for all its serene and frozen beauty, may be quietly guarding the most profound of secrets, a secret that flows in absolute darkness, waiting for us to listen. The search for hidden oceans leads us outward to the wild frontiers of the Uranian system. Far beyond the orderly orbits of the major moons, a motley crew of tiny, unpredictable worlds dances in the distant dark. These are the irregular moons, and their chaotic paths hold a story of cosmic theft. While moons like Miranda and Ariel follow neat, circular orbits in Uranus's equatorial plane, these distant outliers with names like Sycorax, Caliban, and Prospero are celestial rebels. Their orbits are highly eccentric, taking them on long, looping journeys far from the planet, and they are dramatically inclined, often orbiting at steep angles to the system's tidy disk. This wild orbital behavior is the signature of capture. These are not native-born Uranians. They are interlopers, most likely ancient denizens of the Kuiper Belt, that vast reservoir of icy bodies beyond Neptune, which were somehow snared by the ice giant's gravity and forced into permanent, if unruly, servitude. Their existence presents our 16th great mystery, the irregular moons and capture history. The central puzzle is not that they were captured, but how. Uranus's gravity, powerful as it is, operates under strict cosmic rules. For it to capture a passing object outright, that object would need to lose a significant amount of its orbital energy, essentially hitting a celestial break. In the empty space of the modern solar system, there is no natural break. So how did these tiny worlds slow down enough to be caught? Scientists propose two dramatic scenarios from the solar system's violent infancy. The first involves gas drag. In the very early days, the young Uranus was still embedded within the thick protoplanetary disk, a swirling soup of gas and dust. A passing Kuiper belt object venturing too close would have plowed through this dense medium, its motion slowed by friction like a stone moving through syrup. This energy loss could have been just enough to drop it into a permanent, albeit messy, orbit around the growing giant. The second scenario is a gravitational three-body tango. Perhaps these objects did not approach Uranus alone. They might have been part of a binary pair, two small worlds orbiting each other. As this duo passed close to Uranus, a complex gravitational interaction could have occurred. One member of the pair might have been flung away with increased speed, while the other lost energy and was captured. It is a cosmic exchange, paying for one object's freedom with another's imprisonment. Studying these captured nomads is like acquiring a time capsule. Their surfaces, likely dark and reddened by billions of years of cosmic radiation, are probably pristine samples of primordial Kuiper belt material. By analyzing their color and composition from afar, we could learn about the original building blocks that formed in the cold outer reaches of our planetary system, material that has remained largely unchanged since the dawn of the Sun. Each irregular moon is a trophy from Uranus's youth, a silent witness to the chaotic gravitational game that shaped the architecture of our entire solar system. The captured wanderers of the outer darkness orbit a world whose very temperature profile defies common sense. Deep within its upper atmosphere, Uranus holds a paradoxical secret, a layer of shocking heat in the solar system's coldest planet. This is the mystery of the hot thermosphere, high above the serene blue clouds at the very edge of space where the atmosphere thins into nothingness. Temperatures soar to a blistering 800 Kelvin, nearly 1,000 degrees Fahrenheit. This is hotter than the surface of Venus. The existence of this atmospheric furnace is utterly baffling. On Earth, our thermosphere is heated primarily by the sun's extreme ultraviolet radiation, a high-energy light that strikes sparse air molecules and gives them a tremendous speed, which we measure as high temperature. Yet for Uranus, the math simply does not work. The sunlight that reaches this distant world is almost 400 times fainter than what we receive. When scientists calculate the heating from solar extreme ultraviolet radiation alone, the numbers fall dramatically short. There is simply not enough energy from the feeble sun to explain such a scorching outer layer. So what invisible fire is burning in the Uranian sky? Astronomers are investigating two compelling and exotic possibilities. The first looks upward to the chaotic magnetosphere. As charged particles from the solar wind are funneled along those lopsided magnetic field lines, they can slam into the upper atmosphere, depositing their immense kinetic energy directly as heat. This process, akin to a continuous planet-wide aurora, could be pumping vast amounts of energy into the thermosphere from above. The second theory looks downward into the deep atmosphere itself. Far below, in the dense layers of hydrogen and helium, colossal weather systems and convective motions might generate powerful atmospheric gravity waves. These are not gravitational waves in the cosmic sense, but immense, slow-moving ripples in the air itself, like waves on an ocean. As these waves travel upward into the thinning atmosphere, they can break, much like an ocean wave crashing on a shore. This breaking action dissipates their energy directly as heat, potentially providing a steady, internal furnace that warms the upper layers from below. This energy imbalance is not a minor accounting error. It is a critical missing piece in the planet's entire energy budget. Understanding what heats the thermosphere is essential to modeling the full circulation of the Uranian atmosphere, from the screaming jet streams at the cloud tops to the quiet flows in the deep abyss. It forces us to ask, is the serene blue face of Uranus merely the calm center of a system powered by invisible fires from above and below, a world whose true energy sources remain completely hidden from our view? That hidden furnace in the thermosphere bathes the layers below in a soft, relentless glow of ultraviolet light. This faint but persistent energy triggers a silent, planet-wide alchemy, transforming simple molecules into a complex chemical soup. High above the main cloud decks, in a region called the stratosphere, sunlight acts as a cosmic catalyst. Its ultraviolet photons are energetic enough to smash apart stable molecules, beginning a cascade of reactions that scientists are still striving to map. The primary ingredient in this distant factory is methane. When a methane molecule composed of 1 carbon and 4 hydrogen atoms absorbs a UV photon, it can break apart. The freed carbon and hydrogen atoms do not stay lonely for long. They rapidly recombine with other fragments, building heavier and more complex hydrocarbons. Acetylene, a molecule with 2 carbon atoms triple bonded together, is a major product. So is ethane, a 2-carbon chain, and even diacetylene, a 4-carbon molecule. This process, called photochemistry, is a slow but relentless assembly line running continuously across the sunlit hemisphere of Uranus. The end products of this invisible industry are not gases forever. As these newly minted hydrocarbons drift into colder, higher layers of the stratosphere, they condense. They form tiny, solid particles of ice and soot, a fine mist of complex organic compounds. This is the origin of the global haze that shrouds Uranus, giving it that featureless, pale blue complexion by scattering light uniformly and masking the storm clouds below. The great mystery lies in the details of this planetary-scale laboratory. What are the exact chemical pathways? Do reactions happen in 2 steps or 10? How quickly do these hazes form, and what determines the size and composition of the final particles? Even more puzzling is the question of transport. Uranus's powerful zonal winds are confined to a deeper weather layer. The stratosphere above is thought to be much calmer. So how does the haze, produced primarily on the sunlit side, get distributed evenly across the entire planet, even over the winter poles shrouded in decades of darkness? There must be slow, planet-encircling circulation patterns in this high-altitude realm, gentle winds. We have never directly measured that act as a global delivery system for this photochemical smog. Understanding this process is more than academic. Uranus serves as a natural model for a class of planets we are now discovering by the thousands, cool gas giants and ice giants orbiting other stars. By deciphering the chemical factory in its stratosphere, we learn how organic hazes form on worlds with methane-rich atmospheres. These hazes can dramatically affect a planet's climate by absorbing or reflecting sunlight, and they might even shield the surface of smaller, rocky worlds from harmful radiation. The bland face of Uranus, therefore, is not a blank slate. It is the finished product of a billion-year-old chemical industry, a veil woven from sunlight and methane, hiding its secrets in plain sight. That global haze is a mask for deeper gravitational rhythms, a silent music played between worlds. Orbiting Uranus are moons caught in a precise celestial dance, their movements linked by simple, elegant ratios. This is the mystery of the orbital resonances. Take Miranda and Ariel, 2 of the planet's most geologically scarred moons. For every single orbit that Miranda completes around Uranus, Ariel completes exactly 3. This is a 3-to-1 orbital resonance, a gravitational lockstep that repeats with clockwork precision. Such resonances are not unique to Uranus, but they are powerful fingerprints of the system's history. When moons are locked in resonance, their gravitational tugs on each other reinforce at the same points in their orbits, like pushing a child on a swing in perfect rhythm. This repeated rhythmic pulling does not just maintain the orbital pattern, it transfers energy. This energy manifests as tidal heating, flexing the moon's interiors through friction. The resulting heat can be transformative, enough to melt ice, drive geological activity, and potentially maintain subsurface oceans for eons. The dramatic, fractured landscape of Miranda and the vast canyon networks of Ariel stand as stark monuments to this possibility. Their tortured surfaces scream of a violent, energetic past, and tidal heating from orbital resonances is a prime suspect for providing the necessary power. Yet the mystery deepens when we ask about timing. Are these moons in resonance today? The current orbits suggest some are, but the gravitational puzzle is far from static. Moons do not form in perfect resonance, they fall into them over time. As moons interact, they can slowly migrate, drifting inward or outward due to subtle gravitational nudges and tidal forces from the planet itself. This migration is the key to the entire dynamical history. A moon like Miranda may have crossed several gravitational milestones, falling into and then out of powerful resonances with Ariel or Umbriel over billions of years. Each crossing would have been a geological cataclysm for that small world, a period of intense tidal heating that cracked its crust and created its bizarre coronae, followed by a long freeze as the resonance was broken and the internal fires died. Unraveling this history is a detective story written in gravity and orbital mechanics. Scientists must work backwards, using the present-day positions and properties of the moons to simulate billions of years of gravitational interactions. It is an immensely complex calculation, as the tiniest change in a moon's initial position or composition can lead to a completely different evolutionary path. The resonances we see today may just be the latest chapter in a long, chaotic novel of gravitational encounters. Did these dances drive the eruptions that created Ariel's smooth plains? Did they provide the catastrophic flexing that shattered Miranda and then pulled it back together? The moons themselves are the only witnesses. Their scarred surfaces a cryptic record of gravitational rhythms that have echoed through the darkness for ages. The silent gravitational rhythms that sculpt the moons may also be painting the face of Uranus itself with a subtle, shifting brush. Our 20th great mystery is a celestial case of two faces, an asymmetry in reflectivity known as the Bond albedo. When Voyager 2 flew past in 1986, it captured a world in southern hemisphere summer. The data revealed a curious detail. The southern half of the planet was slightly brighter, reflecting a tiny bit more sunlight back into space than the northern half, which was deep in its decades-long winter. This is not about color. Both hemispheres share that pale blue hue, but about the sheer amount of light bounced away. This imbalance in overall reflectivity is a clue written in light, and it points directly to the planet's extreme seasons. The leading suspect is the planet's own photochemical shroud. Remember the global haze, that mist of complex hydrocarbons created by sunlight breaking apart methane. The theory is straightforward. The hemisphere experiencing continuous summer sunlight for years on end has more intense photochemistry. This could be generating a thicker, more widespread haze layer, which scatters sunlight more efficiently and makes that hemisphere appear brighter from afar. But the mystery is far from solved because other players are on the stage. Is the difference actually in the methane clouds themselves? Perhaps the summer sun drives more convection, lofting more bright methane ice crystals higher into the atmosphere to form a more reflective cloud deck. Or could it involve the deeper, smellier layer of hydrogen sulfide ice? Seasonal changes in atmospheric circulation might alter how these darker or lighter ices are distributed, subtly changing the planet's overall mirror-like quality. The only way to solve this puzzle is through patience, a kind of cosmic watch spanning human lifetimes. We are now entering a pivotal era. The northern hemisphere, which was in darkness during the Voyager flyby, is now coming into its own long summer. If the asymmetry is truly seasonal, we should witness a grand reversal over the coming decades. The north should gradually brighten, becoming the more reflective face, while the south dims as it plunges back into winter darkness. Astronomers are already monitoring this slow transformation with telescopes like Hubble and powerful ground-based observatories, looking for the telltale signs of change. Confirming this flip would be a monumental discovery. It would prove that the faint whisper of sunlight over decades can repaint an entire world. It would show that Uranus, for all its internal quiet, has a climate system of profound and patient complexity, a world where the weather is not measured in days but in generations. Even as sunlight slowly repaints the planet, an invisible wind is blowing away its very essence. The thin, scorching upper atmosphere of Uranus is not a permanent boundary, it is a leaky sieve. All worlds with atmospheres, including our own, slowly bleed gases into the void, a process called atmospheric escape. The lightest element, hydrogen, is the easiest to lose, as individual atoms can gain enough energy from sunlight or collisions to reach escape velocity and fly off into space forever. For Uranus, this slow bleed presents our 21st great mystery, the rate of atmospheric escape. We simply do not know how fast it is happening. The process is poorly constrained, a major gap in our understanding of the planet's life story. The central question is one of scale. How significant has this loss been over 4.5 billion years? Could this steady trickle have removed a meaningful fraction of the planet's original atmosphere, subtly changing its composition? The unusual geometry of Uranus throws a massive wrench into any simple calculation. That lopsided, tumbling magnetic field complicates everything. On a planet like Earth, the magnetic field generally acts as a protective shield, deflecting the solar wind and corralling the atmosphere, reducing the rate of escape. But at Uranus, the shield is chaotic. The field's wild orientation might actually funnel the solar wind into the upper atmosphere in some regions, energizing particles and dramatically enhancing the loss. In other areas, it might provide temporary protection. It is a chaotic, hour-by-hour influence that is impossible to model from Earth alone. To understand the escape rate, we need precise knowledge of two key factors: the temperature of that hot thermosphere and the exact processes that give particles their final, liberating kick. Are particles primarily heated by breaking atmospheric gravity waves from below, or by charged particles slamming in from the magnetosphere above? Each energy source would create a different pattern and rate of loss. This is not just about hydrogen. Helium, the second lightest element, is also susceptible. Because helium atoms are slightly heavier, they might be lost at a different rate than hydrogen over geological time. If helium escapes more slowly, it could become slightly enriched in the remaining atmosphere. Conversely, if certain processes preferentially eject helium, the atmosphere could become depleted. Detecting a subtle imbalance in the hydrogen-to-helium ratio compared to the Sun's original composition would be a direct clue to this billion-year-long leak. A future spacecraft orbiting Uranus could finally measure this exodus directly, sampling the particles as they stream away. Pinpointing the escape rate is more than accounting. It is a window into the planet's evolution. It tells us how an ice giant's atmosphere weathers the eons under a faint sun and a chaotic magnetic sky, slowly transforming under the relentless, gentle pressure of space itself. That slow leak of atmosphere is a whisper against the deeper, rhythmic pulse of the planet itself. Even something as fundamental as the length of its day remains an enigma. Determining the exact rotation period of Uranus is a task that sounds simple, but proves maddeningly complex. For Jupiter and Saturn, we can simply clock the movement of prominent cloud features or listen to the steady radio pulse generated by their orderly magnetic fields. Uranus offers no such clarity. Its bland, hazy face lacks persistent markers to track, and its magnetic field does not pulse with a clean, regular beat. Instead, it wobbles. The best estimate we have, about 17.24 hours, comes from monitoring the chaotic swing of that lopsided magnetic field as the planet turns. But here is the profound uncertainty. Does the wobble of the magnetic field truly match the spin of the planet's hidden heart? The magnetic field is generated in that slushy, conductive ocean relatively close to the surface. That entire layer could be sliding slowly over the deeper interior, like the outer part of a spinning egg sliding around the yolk inside. This means the 17-hour wobble we measure might only be the rotation period of an outer shell, not the true, fundamental spin of the planet's solid core. The rotation period is not just a stopwatch number, it is a foundational parameter. It is essential for calculating the planet's true shape, its internal distribution of mass, and the dynamics of its deep winds. Getting it wrong means our entire model of the interior structure could be built on a shaky assumption. How do we solve a mystery when the planet refuses to show us its core? Future missions will need to become celestial doctors, using precise gravity measurements to feel the planet's pulse. As a spacecraft orbits Uranus, tiny fluctuations in its path, caused by lumps and valleys in the planet's gravitational field, can be mapped. The pattern of these gravitational bumps is locked to the rotation of the planet's dense interior. By finding that pattern, scientists could finally time the spin of the core itself. Another hope is to detect a faint, repeating radio signal generated by some deep, unknown process within the core or inner mantle, a signal that cuts through the noise of the chaotic upper magnetic field. Until we have that direct measurement, the fundamental rhythm of this ice giant, the steady beat of its hidden heart, remains a guess in the dark. The steady beat of a hidden heart is mirrored in the faint, rhythmic collisions of dust and ice. Orbiting Uranus is a dark, delicate system in a state of perpetual, slow-motion violence. This is the mystery of the ring particle collisions and evolution, a story written not in stillness but in countless tiny impacts. The rings you see in a snapshot are an illusion of permanence. In reality, they are a dynamic, churning arena where particles ranging from house-sized boulders to grains of fine powder are constantly bumping, grinding, and shattering against one another. Every hour, every minute, micrometeoroids from the outer solar system, tiny specks traveling at incredible speeds, slam into the ring material. These impacts vaporize tiny patches of ice, kick up clouds of dust, and slowly, inexorably, erode the rings from within. It is a process of steady attrition, a celestial sandblasting that should, over millions of years, grind the rings down to nothing and cause them to spread out into a featureless disk. Their very existence today, with such sharp, defined edges, tells us this erosion must be counteracted by some form of replenishment. This balance between destruction and renewal lies at the heart of a fundamental question: how old are these rings? Are they primordial, dating back over 4 billion years to the chaotic era of Uranus's own formation? Or are they a relatively recent and temporary spectacle, perhaps the glittering debris from a moon that ventured too close and was torn apart by tidal forces only a few 100 million years ago? The profound darkness of the ring material offers a crucial clue. Their charcoal black hue is not a natural color for clean water ice. It is the signature of relentless radiation processing. Over immense timescales, the bombardment by charged particles and cosmic rays from Uranus's magnetosphere breaks molecular bonds in the ice. This slowly bakes the surface of every ring particle, transforming it into a dark, carbon-rich crust, much like leaving a piece of bread in a toaster for 1 million years. The darkness we see suggests the rings have been subjected to this radiation bath for a very, very long time, leaning toward the ancient primordial hypothesis. Yet the same collisions that destroy also create. When larger ring particles collide, they do not just vanish, they fragment into new, smaller pieces, replenishing the population of fine dust. Some scientists even speculate that unseen moonlets embedded within the rings themselves might be periodically shattered by impacts, injecting fresh material into the system. The rings of Uranus, therefore, are not a frozen monument. They are a living, breathing ecosystem of gravity and collision, a delicate equilibrium between the relentless forces of space that seek to destroy them and the hidden processes that work to rebuild. Understanding this balance is not just about one planet. It gives us a universal key. By modeling how ring particles collide, grind, and darken here, we can interpret the faint rings glimpsed around distant worlds in other star systems, helping us to read the history of those alien planetary systems written in their own circles of dust and ice. The serene, almost boring face that greeted Voyager 2 has not aged well. Our 24th great mystery confronts a stark contradiction in time: the quiescent nature observed in 1986 versus the stormy planet we see today. The single snapshot from our only visitor painted a portrait of profound calm, a featureless blue marble drifting in silence. For decades, that single data point defined Uranus in our minds as the solar system's quiet, dormant giant. But modern telescopes have shattered that illusion, revealing a world capable of erupting with colossal bright storms and swirling polar vortices. So, which image is the truth? Was Voyager 2 simply unlucky, arriving at the precise moment in an 84-year orbit when the planet's weather decided to take a decades-long nap? Or are we, right now, witnessing something unprecedented? A genuine seasonal awakening as sunlight floods back into a hemisphere that has not seen the sun in 42 years. The answer lies in the agonizing slowness of the Uranian year. Voyager flew by during the southern hemisphere's high summer. The South Pole had been baking in continuous sunlight for years, while the North was locked in its endless, deep freeze of a winter. This extreme setup might have created a bizarrely stable atmospheric configuration, a temporary equilibrium that suppressed large-scale storm formation just as our probe arrived. It is as if we snapped a picture of a sleeping bear in mid-hibernation and declared the species perpetually docile. Now, as the planet approaches equinox and sunlight reaches the equatorial and northern regions, we are seeing that bear wake up, stretch, and become active. The bright storms in the north and the intense polar vortex are likely the first stirrings of this seasonal shift, a planetary-scale climate change event unfolding in ultra-slow motion. This highlights perhaps our greatest handicap, a fundamental lack of long-term baseline data. For a world with seasons longer than most human lifetimes, a single flyby is less than a blink. We have no continuous record of its cloud patterns, temperature fluctuations, or storm frequency across even one full Uranian season. This makes it nearly impossible to distinguish what is a predictable, seasonal event from a random, chaotic outburst. Is a giant storm that appears today part of a regular 42-year cycle, or a once-in-a-millennium freak event? Without watching for decades, we cannot know. Solving this mystery requires a patience that stretches beyond individual careers, a collective astronomical vigil to finally understand the true, dynamic heartbeat of this most enigmatic ice giant. The portrait of Uranus is painted with a single, 38-year-old snapshot, a blurry Polaroid from a speeding car. This brings us to our final and perhaps most profound mystery, the desperate need for a new mission. All 24 puzzles we have explored, from the tilted axis to the hidden oceans, share a common root, a fundamental ignorance born from distance and time. Our knowledge rests on the shoulders of a brief encounter. Voyager 2's flyby in 1986 was a historic glimpse, but it was just that, a glimpse. It lasted mere hours as the spacecraft hurtled past, capturing data from only one hemisphere during one unique seasonal moment. We have been trying to solve a four-dimensional puzzle with a single, two-dimensional piece ever since. The greatest unanswered question about Uranus is not written on its surface, but in our own lack of vision. What would we see if we finally went back and stayed? This is not a question of if, but when. The scientific community has rallied around a clear path forward, the Uranus Orbiter and Probe, a flagship mission concept championed by NASA. This would not be another fleeting visitor. The plan is to send a sophisticated orbiter on a multi-year journey, one that would slip gracefully into orbit around the ice giant and become its first artificial moon. From this stable vantage point, it would perform a symphony of measurements impossible from Earth. It would map the planet's lopsided gravity field in exquisite detail, finally revealing the precise layering of its interior, from the possible superionic water ocean to the dense rocky core. It would chart the chaotic tumble of the magnetic field in real time, tracing its origin deep within the planet's slushy mantle, and it would carry a precious cargo, an atmospheric probe. This armored vessel would plunge into the cyan haze, descending through the layers of methane and hydrogen sulfide clouds, tasting the air with its instruments as it fell. For the first time, we would have a direct measurement of the noble gases like helium and neon, isotopes that act as a birth certificate, telling us exactly where and how Uranus formed in the early solar system. The revelations would extend far beyond the planet itself. The orbiter's cameras, far more powerful than Voyager's, would turn their gaze to the enigmatic moons. It would map Miranda's coronae in high definition, searching for clues of past tidal heating. It would measure the subtle wobble of Teutonia and Oberon, listening for the gravitational signature of a subsurface ocean sloshing beneath the ice. It could discover dozens of new shepherd moons sculpting the dark rings, and perhaps even find faint new rings themselves, relics of ancient collisions we have not yet dreamed of. Every flyby would be a mission of its own, transforming these distant points of light into complex, individual worlds with their own stories to tell. Speculating on what it might find is the ultimate exercise in cosmic curiosity. The probe might sniff out unexpected organic molecules in the stratospheric haze, complex chemicals formed by eons of photochemistry. The orbiter might witness the eruption of a planet-spanning storm, finally catching the Uranian climate in the act. It could confirm that one of the major moons not only has a hidden ocean, but that this ocean is in contact with a rocky, geochemically rich seafloor, a potential habitat in the deep freeze. Or it could discover something entirely unforeseen, a phenomenon that rewrites our textbooks on planetary science. The mission to Uranus is not about checking items off a list. It is about opening a door to a realm of fundamental mysteries, answering questions we have asked for decades and discovering questions we do not yet know how to ask. The final great mystery of Uranus is the one we hold in our own hands, the decision to reach out, to go back, and to finally see this tilted world not as a blurry snapshot, but as a living, breathing member of our solar system family. Uranus stands as a testament to cosmic contradiction. This journey has taken us through 25 profound puzzles, from a world knocked completely on its side to a magnetic field born in a slushy, off-center ocean. We have encountered a planet radiating almost no internal heat, yet crowned with a swirling polar vortex and torn by supersonic winds. We have explored dark rings shepherded by unseen moons and scarred satellites like Miranda that look utterly shattered. Every layer of this system, from the scorching hot outer atmosphere to the possible hidden seas within its largest moons, defies simple explanation. This is not a boring blue marble. It is a dynamic, challenging world, an ice giant that actively resists every category we try to place it in. The sheer number of unanswered questions is a clarion call for a new mission, a dedicated orbiter and probe to finally give this forgotten giant the attention it deserves. The answers to these mysteries do not just tell us about Uranus, they rewrite the story of how all planets, including those around other stars, are born and evolve. So, which of these 25 cosmic riddles fascinates you the most? Was it the violent collision that tipped the planet over, the possibility of hidden oceans on Titania, or the silent, dark rings? Let us know your thoughts below and subscribe to join us as we continue to unravel the deepest enigmas of our solar system and beyond.